definite integral. Definite integral is important because it can be used to calculate the area under a curve. It uses rectangles that does not have the same base length to calculate the area under a curve. So recall when we used to use right point, left point, and midpoint formula to calculate the area under a curve using rectangles that have the same base length, so that equal delta x. Now, these requirements can be relaxed, and we can now use rectangles that have different delta x's. So the definite integral over the points a and b is the limit of the Riemann sums. And the Riemann sum has a few important notations that we need to understand. So P represents the partition size of n, C is the sample points in a subinterval. So you can see P, C here, and C here again. So this notation right here is the norm of P, which is the max length of delta x. So what Riemann sum ultimately is saying is that we are now using rectangles that does not have the same base length to calculate the area under a curve. Now here we have a theorem, and the theorem reads that if fx is continuous between interval a to b or has a finite amount of jump discontinuities, then the interval of fx over interval ab can be obtained. So if we have a graph that is continuous and has a finite amount of jump discontinuities, then we can use the integral to calculate the area under it. So now let's say we have a curve like this. A graph like that, okay. So this one's a little tricky because let's say our interval is from here, A here, to B right here. We have a portion of the graph that is above the x-axis and a portion of the graph that is below it. Now this is a very important thing that we have to remember, is that the area above the x-axis is positive and the area below it is negative. So our conclusion should be that the area above x-axis minus area below x-axis can give us the total area. So we have to really remember that the area below the x-axis is negative, and it takes away from the total area, and it's not adding on to the total area. Now let's look at some more examples. So here we have a basic graph, and we have the interval from 2 to 4, and we have function f(x) equals 4. So we plug in the interval. The first interval is always in the bottom, so 2 is in the bottom and 4 is on the top. And then we find the integral of that. And we know the integral is the antiderivative, and the antiderivative of 4 is 4x plus c, c being a constant that we don't know. But in this case, when calculating the area under a curve, it's not that important. And so to calculate this, we will plug 4 in first and then subtract it by plugging 2 in. So we have 4 times 4 plus c minus 4 times 2 plus c. And I say c, the constant, is not that important because it will cancel out since there's a subtraction symbol right here, and the c's are both inside these two brackets. So we have here 16 and here 8. And our area should be 16 minus 8, which would be 8. And now let's verify that using a more traditional method. So we know that the interval is 2, and the height of the rectangle is 4. 4 times 2 equals 8. So the area is confirmed to be 8, and that does match the answer we got from using definite integral. So we know that definite integral is correct. But let's move on to two more complicated ones. So here we have two exactly the same equations, except one is the absolute value of the other. And we know that absolute value graphs never crosses the x-axis, so it kind of just goes to the point that intersects it, so at 2, and then it bounces back up. And these two, as we talked about before, this one would have here displays a positive area, and below the x-axis a negative area. However, this one would have a positive area here and a positive area here. So this graph here should have more total area given the same intervals, right? Now we can really solve this very easily using our knowledge of triangles, because it's just two right triangles here and two right triangles here. But I did solve it using definite integral just to make it a little clearer to you guys. So we have our interval 1 to 3, and then I calculated. So the first graph would be eventually come to an area of 0, and that is pretty much, you can pretty much tell because we do have a slope of 1 and the graph intersects at 2 and our interval is between 1 and 3, so we should come to this, these two areas should be the same, so this answer does make sense. And now we can easily tell that this should be 3 over 2 plus 3 over 2, because these two are above the x-axis, and that will give us the total area for this graph, for this one, right? And so there it should be 6 over 2, which is 3.